Hello, welcome to a short video about free body diagrams. This video is intended to briefly review what a free body diagram is, what it needs to include or must consist of, and then briefly describe their usefulness in the world of engineering mechanics. This textbook on the subject of statics by Miriam, Craig, and Bolton describes free body diagrams as key to the understanding of mechanics because by using a free body diagram, we can clearly see the cause and effect of forces on a body separated from its surroundings, and we can then focus on the application of the principles of mechanics. So out of your study guide, you can see the list of what must be included in a free body diagram. And rather than remembering or memorizing a list, if we just think of what the name free body diagram implies, that'll help us remember quite a few of these items right off the bat. First of all, it's a diagram, or it's a drawing of a body that is free or isolated from its surroundings. And so it must include that isolated body. Then we'll show any loads that are acting on that body as force or moment vectors. We'll also show reactions at the support locations on that isolated body, again as force or moment vectors. We need to include a coordinate system that enables our communication of direction when we're talking about these various vectors, and then we'll also need to include any relevant dimensions. We may also want to include labels as well on our free body diagrams. Now before we dive into a quick example, let's just remember what is meant by loads and reactions and how they differ. A load is an external force or moment acting on the structure. Examples of this include what? The weight of the structure itself. Perhaps loads on a structure. The weight of my body on this floor is a force or a load acting on the structure. Automobiles driving over a bridge, wind blowing against a building, for example. These are all examples of loads acting on a structure, which differ from reactions at the supports. Reactions are forces and moments that restrain or resist translation or rotation, which is the purpose of these physical reactions. These physical supports. So let's walk through a couple of quick examples. First example we'll take a look at is in this image right here, which is a load test of a jib crane. And what you'll see is this is a 2-ton jib crane. It's being tested with 4,000 pounds, which means that jib crane is now at its full capacity. So if you're the engineer responsible for preparing for this test, wouldn't you like to know with some certainty ahead of time that the load test is going to be successful? What would we need to calculate about this jib crane based on that 4,000 pound load to confirm that it's going to be adequate? For this example, we would probably be most interested in what are the reaction forces at these two supports, and can the structure that this jib crane is attached to handle those forces and moments. So let's draw a free body diagram of the jib crane isolated from its surroundings. There it is. Nothing too fancy. It's just the jib crane itself, isolated from its surroundings. We haven't included the little motor attached to the crane or the lifting device at the end of the crane. We haven't drawn the supports themselves. We have isolated that jib crane completely from its surroundings. So we have taken care of this first item on our list of what a free body diagram must include. Next is the loads. What loads are acting on this jib crane? We could include the self-weight, but what we'll find is in most structural engineering applications, the weight of the structure is negligible, and so we often remove it and don't consider it in most of our calculations, at least preliminarily. So the only other load that's acting on this is the weight of that 4,000 pound concrete block hanging out at the end. And we can represent that with a force vector acting down, as obviously the weight would be acting, and label that as a 4,000 pound load. That's the load acting on the body. How about the reactions? What reactions at the support locations do we need to include? Well, if we look closely at this image, or if we pull up the user's manual for this particular crane, we can see that both of these are pins. This location and this location, pin supports. So a pin support does what? It resists translation but allows rotation. So if it resists translation, that means there must be a reaction force resisting that translation. So we know that we must have a force acting horizontally and a force acting vertically at that pin. Now, which way to draw these force vectors? In general, we assume positive. Which way is positive? We've got to have a coordinate axis system to answer that question, so let's include now our coordinate axis system. Pretty traditional orthogonal coordinate axis system, x and y directions. And with that, we can now assume a positive direction on both of these force vectors, and we need to label them. We don't know what the magnitude of these force vectors is, so let's just label them with a variable. We'll call this the force at the top pin acting in the x direction, and this will be the force at the top pin acting in the y direction. We then have the exact same types of force reactions at the bottom pin. So again, we have a force acting in the y direction and a force acting in the x direction. So we now have our isolated body, our loads acting on the body, and the reactions. We've got our coordinate axis system noted here. The only thing we're now missing are relevant dimensions. So we could either use our tape measure, go back out to the Jib Crane and measure it ourselves, or we could pull down the user's manual. Either way, we can find out that the dimension from the very end of this Jib Crane to the pin is 17 feet. And the distance between the two pins is 7 feet. Are there any other relevant dimensions that we need to include? We could measure the width of each of these pieces, but we'll find that for this application of equilibrium, those dimensions are not necessary. Could we add additional labels? Perhaps. Maybe we would want to label points A, B, and C to more easily communicate. Those are optional things. In this particular case, I chose to use a subscript T for the top pin and a subscript B for the bottom pin. So that is a quick review of Freebody diagrams, what they need to include, and one example of this particular Jib Crane that was tested at 100% capacity.